Excellent. So I'm here to talk about some preliminary work we've been doing in greenhouse gas sensing using small UAS. Basically, what we're looking at these UAS platforms, the small class, you're talking about mid-scale to small spatial scale monitoring. And basically what I'm seeing out there is that the utility of these is very much limited by what sensor is available. So we're talking about the 5-pound type UAS and the sub 55-pound UAS category. So when you talk about fugitive emissions and gas sensing using UAS, it's a pretty dynamic environment where you've got common goals across diverse sectors. So we've got energy company interest in this technology, regulatory agencies very interested, and also science of global environmental change with point sources of fugitive emissions a big interest, and our main JPL interest. So our toolkit here that we're going to be talking about, it's an advanced gas sensor that weighs about 200 grams, a miniature CO2 or methane sensing technology, and then we're talking about the small UAS. And what we're operating now is in the micro class, so we're talking about 5 pounds total weight. And our strategy here in this work is the concentration in a 3D field. Then we're translating that in our current work to localizing where the point source is coming from, and then flux estimation is our work next year and into 2016. So Lance Christensen, who's actually part of the MSL, Tunable Laser Spectrometer team, he's a PI at JPL. He was funded back in the 2008-2010 timeframe to make a miniature CO2 sensor, and that was funded by NASA as part of the NASA Upper Atmospheric Research Program. So what you see in the middle there in the diagrams, you're looking at the sensor, our sensor prototype on the left-hand side, and then a schematic on the right-hand side. So we're talking about a 5-inch cell. It's a Harriet cell technology with miniature components and onboard electronics that actually do the data processing on board the sensor. And this is called the Open Path Laser Spectrometer, and we've got a CO2 version and a methane version that we've developed. I mentioned the original version was for CO2 detection. The methane version is the newest iteration that we've done, and that was funded in part by energy companies to help spur that development. We're talking about a 200-gram version, and the integrated electronics, like I mentioned, are on board, and we're getting a 10 parts per billion sensitivity with this sensor. So we're talking about an order of magnitude less sensitive than the big rack mount systems that people are commonly using on aircraft and in vehicles. So pretty impressive for a payload this size. So our focus here is on methane. It's with the methane sensor that I mentioned. And what we're trying to do here is offer a technology to help constrain the concentrations and eventually the flux rates from these point sources that are recognized to be a very large input mechanism to the North American and global greenhouse gas budgets. So if you look at the figure on the upper right-hand side, this is a pie chart. It looks very clean. The error bars there are actually huge when it comes to each of those relative contributions. We're talking about animal husbandry being a huge input mechanism, and also the anthropogenic inputs from natural gas and petroleum systems, a potential large source. So I should mention the focus on methane is very timely, especially this week. So the investigator Lance Christensen is also part of the MSL science team, like I mentioned, and they just announced their positive detection of methane on Mars, which is exciting. So it's very great to see this work as a corollary demonstrating this for Earth science and global environmental change. So on the lower left-hand side, what we've done in this past year is we've actually used this sensor for handheld leak detection, which I'll talk about in the next slide briefly. And then going back to 2013, we did some deployments on the small UAS. So the handheld leak detection, what we've done so far is we've looked at a number of different sources. And I'm just sharing 2 of those right now. We've done some walking surveys at a landfill location in Southern California. And you can see during this walk-around survey, you can see the intensities from this tunable laser spectrometer up to about 25 parts per million above background. And then there's also a simulated leak experiment we've done to show relevance for leak detection in the real world. So you can talk about enhancing safety for downstream oil and gas operations. What you see in the lower right-hand side is actually a walking survey where we had controlled releases in this simulated neighborhood. And you can see the data products there that can help us track and pinpoint leak locations. So on to the Quadrotor work that we've done. We're using a vertical takeoff and landing system. The total mass of this Proceres UAS is just 5 pounds, actually. So the sensor itself, another 200 grams, which is a good size payload for this type of vehicle because you're not cutting into the flight time too much. So we're talking about up to an hour flight time using this system. And going into the 2013 results in a moment here, I just want to show one of our little simulations of how this could be used, what our goal is to really help constrain these methane budgets. So what you're seeing here is just flights around a pretty densely populated oil field with one or more of these platforms. They're coming in, flying a repeat circuit, and able to look at the concentrations, and also able to look at the spatiotemporal variability of these systems. So our science technology goal of our 2013 demonstration was a proof of concept using this Opals laser spectrometer on our VTOL platform. Then we wanted to look, using a controlled release setup, a variety of flux rates and what the sensor signals were well downwind of this controlled release. And then characterize performance and also moving forward to a system solution to address this technology science goal. So what we did here is we flew a couple of different flight patterns. We had a methane-controlled release point. We had an atmospheric or a 15-meter tower that we had downwind of the release point. If the wind changed, we would move the controlled release point to be directly upwind from the tower. Then we would fly these patterns using our sUAS. And there's a linear flight pattern and the grid flight pattern that I'll be speaking to quickly. So the linear flight pattern was basically just flying downwind, and a small part of it was done upwind of our release, upwind of the observation towers. And what you can see here, gridded on a 1 ppm delta, is you can see clearly these large events that we're detecting directly downwind from the release points. So that's the linear tower, the linear flight pattern. Now here's the grid flight pattern that we flew also, and you can see the bias. The plume was staying very low on this particular day due to the prevailing winds, prevailing wind speed and atmospheric conditions. So a summary of what we saw here and what data I'll briefly be talking about. We ran our flux rates from 100 to 2,000 standard cubic feet per hour. Those are all pretty large flux rates, but this was proof of concept, so we wanted to be able to demonstrate our signal intensities across a wide dynamic range. We were about 80 meters to 100 meters distant downwind from the release points. And the wind speeds were generally pretty agreeable, pretty low at about 4 meters per second for all of our flight days. So what we're seeing is our threshold of detection. Our poor signal to noise was observed at the 100 SCFH when we were about 100 meters downwind. So that was basically our floor. The 500 SCFH, that's standard cubic feet per hour, about 250 liters per minute. That was our threshold of detection for this particular experiment. So I'll be focusing on 3 flights, the 500, 1,000, and 2,000 standard cubic feet per hour data sets that we collected. And what you're seeing here is the magnitudes of these eddy detection events that you're actually observing here scale pretty well with the flux rate. And you can see a lot of dynamic detections here and a lot at the 1,000 SCFH. Then at the 500, we've got poorer signal to noise, and we've got fewer events that we're observing. You will note, you can always pick up where we left ground. One of the concerns technologically about this sensor is limiting the vibration environment. So you can see our signal to noise increase here. That's typical of the flying with a quadrotor. That's a very dynamic, high vibration environment, and we are addressing that in the next version. So if we look at the 2,000 SCFH, where after takeoff time, we saw a lot of large events. The deviation from background was up to 60 or 70 parts per million, which is a huge detection event there. We can look at the detections as a function of altitude at the different altitudes that we flew. So here is our flight time. Here is our parts per million of methane concentration. Then our altitude, you can see we only went up to about 30, 35 meters, and then down lower. And if we visualize this data as concentration versus elevation, meters AGL, we're just looking at before takeoff, we're seeing actually a lot of those plume events coming over to our takeoff site. Then we're also able to pick out these events, and that indicates where the plume was most focused during this particular 30-minute flight. So you can see it's staying pretty low at the 6 to 7 meter, and the 13 to 14 meter shows a little change in the wind that we observed during this flight. Doing the same for the 1,000 standard cubic feet per hour flux rate. You can see that in this particular environment, only the low flight patterns really picked out those dynamic eddy events that were indicative of a big detection. And also visualizing that in a part per million versus AGL schematic here, you can see that on that day, due to the wind speeds, the plume was staying pretty low the entire time. So what we're demonstrating here, again, proof of concept wise, is we've got a very sensitive 10 ppb sensor that when we fly it on a vibration platform, we lose about an order of magnitude sensitivity. So we've got to remedy that. But also what we're able to do here with just a simple sensor quadrotor configuration is constrain the height. You can see we're still very much unconstrained for projecting where that leak location is coming from and what the flux rate is. And those are our thrusts right now. And I'll talk about what's needed to get us there. In order to project our goals of this sensing technology, we actually had some large eddy simulation runs done by Georgios Mathau at JPL. And what you're looking at here is a 6 standard cubic feet per hour flux rate that he's simulating here. And this is a low-level goal of ours to be able to detect those very small leaks. We were over an order of magnitude distant from that in our preliminary testing. So what you're seeing here, these 3 lines represent the origin of the release point, 50 meters and 100 meters downwind of the point. So you can see at low wind conditions, we're looking at not much dispersion occurring, and you'd have to fly right up against this or very close at low wind speeds to detect this event. At 3 meters per second and 5 meters per second, you get greater dispersion, so it gives you a higher probability of detecting concentrations at 100 ppb above background, well downwind of the release point. And these are the ISO surfaces at 100 ppb background here, which is our detection limit with the current sensor version. So next step, I mentioned we want to go from this XYZ plume concentration detection, this 3-dimensional concentration profile, to leak location and flux rate. So we've demonstrated proof of concept with some pretty robust leak rates. And what we're seeing here is a real good earth science application and future planetary missions. We're going to be sending quads to other planets before we know it. So useful for Mars methane detection and also perhaps Titan deployment. So our signal to noise improvement that we're looking for, the structural and vibration analysis has been done, and we've actually solved in a large part that problem. So our next deployment will test how well we did at giving more rigidity and improving that signal to noise on the vertical takeoff and landing quadrotor platforms. Our field demonstrations, we need more data. This was 3 days of data that we took back in June of 2013. So we're going to be doing at least 4 field demonstrations next year in a variety of different locations. Now the fixed wing deployment, that's also an interest of ours. That gives you capability to monitor larger areas because those systems are more efficient than quadrotors. So we're always looking for opportunities to collaborate for fixed wing deployments using these technologies. And I should mention the vibrational issues that we observe in the quadrotor are not anticipated to be problematic on fixed wing deployment. And I will highlight, I've learned a lot about the wind speed work that's being done on a lot of these small platforms. we need a small 200-gram sensor for wind speed that we can incorporate in this system and the fixed-wing systems eventually as well. Thank you very much. Appreciate your time.